Okay, I think we can start. So thank you again to everyone to be here today. I am Alberto, and I am an artificial intelligence student here at University of Verona. And today I will try to provide to you a general idea about what reinforcement learning is and about how does it work. Lorenzo will help me to make this meeting for what concerns the second part. All this presentation is inspired from this book, which is The Sutton and Barto, and we suggest to you to search on Google the name of the book, and you will see that in the first results there is the PDF edition of the book, so it is free. And substantially today we will introduce the tabular methods algorithms, which are the more basics algorithm proposed to develop an reinforcement learning technique. And okay, probably, usually you just heard talk about supervised and unsupervised models. In the supervised, you have an input and you have an output about which you just know, so which is the prediction that you are attended from a given input to feed to a model. In an unsupervised, you have instead an input, but you don't know which is the attended output that you are waiting for, and so you ensure some clustering algorithms to make this kind of this kind of a separation of the space of your input to understand which kind of input you have in your dataset. Instead, the reinforcement learning approach is completely different from these two old style, let's say, kind of technique. The idea of reinforcement learning is that to learn from experience, but substantially the goal is that of decide which is the best action to perform in a given moment in time. So, for instance, respect to the other techniques where you ask to yourself which is given an input, which is the output that I want to achieve. Here the question is which is the best action, which is the best decision that I have to take in this precise moment to maximize which is my feeling, in some sense, my expected reward that I can achieve in the future. A good example from which start probably is the child example. When we were a child, we were like a reinforcement learning algorithm which has no experience, okay? And so the only way to learn from starting from our actions is that of perform them and see what happens. For instance, if we are hungry, we take food or we drink milk in this case, and we understand that this is the good behavior to perform. On the opposite, if we touch the fire or whatever, if we commit in our life some action against someone other or some we behave in a non-well manner, we achieve a kind of negative reward from the environment, from the real world. And so from the experience, we are able to understand which are the good and which are the bad actions to perform in each moment of our life. Another example is that of if we have an exam, okay, for instance, today is Thursday. We have an exam on Monday, okay? Tonight, I go to a party. Tomorrow, I go to a party, Saturday even, and Sunday too. There is a concept. The concept is that we go to a party and we perceive a reward which is immediately positive because at the party we improve which is our happiness in that moment, okay? But probably if we didn't study, we will fail the exam on Monday. this kind of way of thinking, it's really close even to the reinforcement learning algorithm. Let's make another example which can be more clear maybe. The vacuum cleaner, the so-known Roomba, that maybe you just you just heard talk about, has the purpose of clean all the house, okay? Or an environment in which it is put. But the problem of the vacuum cleaner is that during it is moving, it is consuming battery. So in some sense, it perceives a reward which is negative in the immediate reward, which is the same immediate reward negative that we can feel if we study. On the opposite to go to a party, because if we study, we use effort, okay? And so in some sense, in the immediate, we have a negative reward. But like the vacuum cleaner at the end, after a lot of negative reward in terms of battery charging that is consuming, and as in terms of effort that we perform on study, at the end, in both the examples, we achieve a situation where we have instead a future reward which is maximized. The vacuum cleaner has cleaned everything, and we probably passed the exam if we studied. So this is a concept that it's not so easy, of course, to let this pass in the algorithm, but this is, however, I think that is real, that happens that we have like programmers to take in account. Okay. The basic ingredients for each reinforcement learning algorithm are substantially two. We have an environment and we have an agent. The environment is a world. In this case, in this example, this is the Super Mario game, the environment is given from the game by itself. The environment provides to us states and reward. With states, I mean, in this example, an image, a frame, a picture that describes a time or moment of the game. But in reality, in a reinforcement learning algorithm, a state can be taught like everything you can imagine. A state is something, it's programmatically speaking, is a set of information that you, like programmer, decide, or depending on which problem you are working. A robot, for instance, is perceiving from an environment by a camera, for example, staying in the image example. And substantially, the environment provides to us states and reward. The objective is that the agent, given a states, perceiving rewards, decide to perform the best action which allows the agent to reach the maximum total return in the future. Okay? In reality, here in this example, the agent is Mario, but in reality, we are the agent because we are giving the commands by a joystick. But the idea is, however, that there is an environment which provides to us states and reward. So moment by moment in time of our world is described. Perception about if it is negative or positive, what we done, and an agent that has to decide, depending on what is the final goal, the final scope to achieve, to do. Here we have some examples about how reinforcement learning is really used in real programs today. And here you can see a self-driving car systems where the states you can imagine that is a picture by picture, a frame by frame of the camera, which are captured. And like you can notice, of course, there is a kind of detection of the objects and the distances in some sense that there is between the objects. Given these like states, okay, in input to our algorithm has to decide, with the algorithm I mean in this moment in reality the agent, our agent has to decide which is the best action to perform. So in this case, this is an example where it is turn left, but like you can imagine, in a problem like this, it's necessary that the agent performs the good action, because here it's it could be really dangerous if they're not make the good action. I mean, there are people who can cross the streets. There are objects that can be damaged. So in this kind of environment, of course, in this kind of algorithms for this kind of problem, we need a really care in the implementation. Another example is the Boston Dynamics that probably you just heard talk about them, you just saw, which are more famous in this moment because people are trying to implement reinforcement learning algorithm on the Boston Dynamics hardware. And another example from the robotics field always are the robotics arms, which are in this moment really a lot used in the manufacturing field. Substantially, they grab objects and they decide which to put them. In some sense, usually a kind of machine like that has a camera which perceives states by states what is around them and decide a rotation or a go forward of some engine. And of course, there could be obstacles, there could be people who comes in the middle. So here too again, a lot of care in this kind of algorithm for this application. They are even used in this moment for medical surgery. Once time more here the care is probably this is the maximum field where the algorithm has to work because otherwise it's a problem, like you can of course imagine. And there is another field which usually is not so known, but this is the financial field. In the financial field, for instance, maybe you just heard talk about the robot trading. They are the majority in this moment are reinforcement learning agents, which takes market movements from different assets in a given moment of time and decide how to allocate portfolio assets. So they decide to sell or buy different stocks, and this is used in this moment. If you go to search, there are even papers from JP Morgan about reinforcement learning applied to finance. So in some sense, it's the state of the art. Okay. Now that we've seen a basic introduction of examples about what reinforcement learning is, we'll go a little bit in the detail about about how does it works. Reinforcement learning comes from the mathematical model, also known as Markov decision process, which works plus or minus in the way that I just explained to you before with the Super Mario example. So we have an environment. This environment, programming speaking, is modeled to be some kind of structure, an object, whatever you want, which given an action provides a state in which we are going to reach, okay, like output, and a reward that we take if we are in a given state in a given moment. The agent, taking the states which is provided by the environment, decides which is the best action to perform. Above the agent in the schema in this image, there is the P Greek letter which stands for policy. A policy is in reality probably the core of reinforcement learning because the policy is that function that given a state tell us which is the best action to perform. So the policy is the goal of our reinforcement learning algorithm. When we started to develop a reinforcement learning algorithm, in reality, technically speaking, programming speaking, we wanted to achieve the policy because the policy is that kind of function that given a state tell us which is the best of the best action that we can perform. So how to achieve the optimal policy? This is a good point, which is which is the key point of all the algorithms essentially, where we want to maximize the action of an agent, and the basic idea is that we are going to generate a trajectory, which you can imagine like if I am there, I am to go outside of the door. A trajectory could be that I make step by step. Maybe I do this, but maybe it's not the good idea to do this. I have to go. I have to go straight. If I am there, I have to reach the door. Okay. So this is a trajectory where states by states, position by position, I decide where to put the next foot. And so the idea is that we generate a lot of trajectory with an algorithm, okay? At the start, we don't know which is the optimal policy, we don't know which is the right action to perform, and so it is random, completely random. Okay, to go to the door from there, I can make all around in this room. But trajectory by trajectory, learning from by experience, learning by experience, I will reach a policy which is the maximum between all the other policies that I just computed before. And so in that given moment, we said that we reached the convergence of the algorithm, that there is no other improvements that could be done, and we found which is known as the optimal policy. The concept of optimal policy brings us to the concept of value of a state. A value of a state is better explained in the next slides, and I will explain better in the next slides. But think to it like if it is a function which tells to us the goodness. Just watching a state, just being aware to be in a state, the value function of a state following a policy P tells us how much it's good to be in that given state. And of course, after a lot of trajectory, after a lot of iteration of our algorithm, after a lot of learn, the final results that we want to achieve is to find the maximum value function than all the others that we just computed before. There are two fundamental functions when we speak about reinforcement learning. The one is the value function that I just talked a moment ago, but I will explain it better, and the quality function. The value function, like I said, is the idea that just given a state, we know how much a state is just good by itself. So for instance, here that we are in the Super Mario, like before example, if you just played, probably you just seeing this frame, you just understand that this is the end of a level. And so just the algorithm, an reinforcement learning algorithm, just watching this, just seeing this, it's able to understand that this is good. It's good because this flag indicates that this is the end of the level. So we're reaching the goal in some sense. Okay. Instead, the quality function, which takes as input a state and an action, tells us, given a state, and the state is all this picture for the game, okay? Given an action, and in this case, the action is jump, okay? I imagine that there are two actions in reality, okay? One is jump a bit, and the other is jump a lot. If we jump a bit from this point, we go through an enemy. And so the quality function of this state, given the action from this state, okay, where even Mario is there, jump a bit, will bring him to an enemy. And so this is not good, of course. And the Q function for given this state, given the action of jump a bit, will have a value, numerically value, a numerically value, which is lower than to be in that state, to be Mario, and to jump a lot, so we are able to go over the enemy. This kind of action will have a numerical value which will be higher than the jump a bit. So plus or minus the difference between them is that a value function tells us just this state is good or not. The Q function tells us the state and the action. Always programmatically speaking, you can imagine the value function in all these tabular methods that we are presenting, like if it is an array, a normal array of the dimension of each state that describes our problem, our environment. And instead, you can think to the Q to the Q function like if it is a table where for each state we have some actions that are a priori defined. Infatti mi sembrava che... No, perché mi ha preso il volume. Ok, grazie. Scusa. Okay, so this is a kind of grid war example, which is the most basic to understand what an environment is. And here you can imagine each cell of this grid like if it is a state. Okay, so each square is a state. And this is a state, this is a state. Okay, every cell is a state. Okay. Here we have an obstacle, which is the wall, in which obviously the agent cannot go through. Here we have a dangerous situation, which is the explosion, in which if the agent goes, the episode will stop. And here we have our goal that the agent has to achieve. So in this case, the diamond. This is a framework that you probably will find on GIM, which is a framework for implement reinforcement learning algorithm. You will find something like that for the grid word sample. And the idea is that the agent. So when we define a kind of problem like this, we have the structure to store the states, which are each cells of our environment, a structure to store the actions that are allowed to be performed by our agent, and we have the reward function, which tells to us where if given a state and given an action, which is the reward that we are expected. Let's make an example. If the robot is there, okay, and the action is to turn right, okay, the reward function will provide a -1 because this is a not allowed action to do in this kind of environment. Instead, if the agent is there and the action is to turn right, it will take the maximum reward that is provided. Imagine this like if in real world, in reality here, instead of have the red one, maybe we are a car, there is a canyon on the right. Of course, the car has to, the algorithm which provides the action to the car has to know that it's a bad idea to go down in the canyon because, of course, we will damage the car and probably we will die. So it's important to define a priori which are the rewards that are provided to the agent, of course. Here in the reinforcement learning, we have even another concept to take in account, which is the transition probability. The transition probability could be deterministic or stochastic. Deterministic means if I tell to the if the algorithm tells to the agent to perform an action, the agent will perform that action for sure. All the time that action, a kind of action is told to the agent. But unfortunately, the world is not deterministic. The real world is not deterministic. And so there could be a little bit of stochasticity. The stochasticity tells us that if we if the algorithm tells to the agent to perform an action, in reality, with a certain probability, the agent will not perform that kind of action. Here, the example is that we tell to the agent to go up, but with a certain probability, he decided to go left, and so he go to explode and he die. He decided to go up for real, or he decided to go right. Imagine this like in the Super Mario of before. Okay, in the Super Mario game, there's not properly this condition, but let's imagine that when Mario is jumping, there is the wind. There is the wind. And so, if the idea is that to jump of some length in space, if there is some stochasticity, with in this case the wind, Mario will not go on how much how he desired to do. So, in some sense, it is something that has to be taken account when a reinforcement learning algorithm is developed. Here there is an example of the tic-tac-toe, which explains better the concept of the Q-value. We have crosses and circles. The black one that you see are the given states, while instead the red crosses that you see are what we did a moment ago. So given the black one, which are the states, the action of put a cross here, of course, has a Q value which is measured and put across there. Okay, because here we are ending the game, we are winning, and it's done. Here, instead, we let to our enemy the possibility to put here circles and to do not let us win. So the Q value provides to us a measure given a states of which are the possible scenarios that will happen if we commit different types of action, substantially. For what concerns the concept of the value, instead, this is a better state, okay, than this one. Because here the agent is more near the goal that is aimed to achieve. Instead there, our agent is more near to a dangerous situation, okay? And yes, substantially, numerically speaking, the value of these states is more high than these states. Okay, coming to the real substance about what a value function is. It comes from the Bellman equation, okay? And like I just said several times, the idea of the value function is that to tell us how much is good a given state, given also a policy that we followed. The idea is that we can see that the state is good, okay, making a sum, an averaged sum for the probability to make a transition between a state and another for the reward that we'll achieve going in that states. This is a more simple way to see the formula. This is instead a more the real one. Substantially, if here we have a state S, okay, we try to see what happens in all the other states that we can, S prime, that we can achieve starting from S. We compute the probability of transition, which is this blue one, which is given by the states in which we are, the policy given the states, where this function provides to us the best action that we could perform in the state S, and given the state, given the action, which is the probability to go in the S prime states. All this is multiplied for the red one part, which tells to us which is the probability, which is the reward that we achieve in a state, taking the better action that we can take, and go in the state S prime. Plus, and here there is a really key concept, which is the concept of the future. The gamma here stands for the discount factor. It is a numerical value which lies between 0 and 1. And if we put this value to 1, it's like if we are going to give to all the future rewards the same weights. Like you can notice, for this examination, we are iterating over each next states that we are encountering from S, okay? And here we are bringing in the current states, all the goodness of the next states that we will encounter in the future. So in some sense, it's like we are trying to create a relationship between the moment in which we are and what is the goal that we want really to achieve. This is a way to make a trajectory of if in this moment we are in a state that is the good states, and so we have to continue to the next states of this to achieve the best final goal, which we aim. Or otherwise, it will tell it is maybe want to be a good value, and so will bring the danger to us in the past. It's the concept of before of there, okay? The value function that we computed there depends even on this, okay? Even on this. This, which is in the future, which is in the next state that we can achieve from there, this is bad, okay? So it is important for us just in these states to be aware that we have not to go up, because if we go up, it's a disaster. Here, this is a fake example. In the real world, is a car that go in the canyon, that go against a wall, okay? This is the pseudocode of I will introduce now two dynamic programming algorithms, which are used to compute the value and the policy, and this is the value iteration. Let's think about this a moment. Okay, so what we do at the start is to initialize the VS function, and in this case, because we are in tabular methods, we are working with a discrete environment, it could be represented like an array, a simple array, programmally speaking, where we have which has the size of all the states that we have in our environment. So, for instance, of before that we had the gridboard 4x4, we have a VU array which is of 16 values. At the start, they are arbitrarily generated, so it means that they are random substantially, except for the last, which is 0, because the algorithm stop. The idea of the value iteration is that to iterate over each states that we have in our environment. Imagine at the first step of this algorithm, we store in the little capital V, a random value. Okay, so this probably will not work for sure. Now we start for each next states that we can achieve for the states that we are iterating now. Here there is even an iteration on all the action because we want to select which is the maximum. So here it's not right, but it's like if we iterate over the action 2. We compute which is the value function, okay, given an action, given these states. What happens there is that we output another array from which we are going to select which is the maximum action. So we are going to update, given this formula, the one that has the future, okay, the one that has the future, which is the best. And we are going to put this in our current value function of the states. After that, the delta parameter starts to 0, so here at the start we have the maximum between 0 and at the end. Here there will be a big difference because this is random and this is just generated from real interaction with the environment, so probably the difference between a random and a real will be bigger. After a lot of iteration of this kind of algorithm, the good situation will be that the difference between the old one that we are storing every time that when we restart to iterate with the states and the just computed should be less, should be little, should be really little. At this point, we reach the convergence. And the moment when we reach the convergence, what can we do? We compute, which is the policy. Because now we have the good value function. And so now we are able to compute which is the best action to perform. This is like before a variation of the Bell equation formula. Here we have the usually probability of transition multiplied for the reward that we take in a given state for how much is good even the future that you are taking account. The only difference, like you can notice, is that here, because we are always in tabular methods, the value is a max, okay? So the value is properly a number. Usually it is a float number, okay? Instead here, their max is an index, so we select an integer number. This is why, because imagine the action of before, which was left, right, up, and down. We can map them like if they are 0, 1, 2, 3, programmatically speaking. This is the policy iteration. The policy iteration is quite similar, a little bit different. The difference between the value iteration and the policy iteration is that the policy takes in account even to try in reality the policy on the environment. So really fast. The idea is that we initiate a value function, which has the dimensionality of our states that we have in our environment. We defined always an arbitrary policy, which is always a vector which tells to us, given a state, so given a position of the policy vector, which is the index of the best action to perform. We implement the policy evaluation, which evaluate over each states that we have in our environment. We store the first random. We compute the new. We check for the convergence. If not, we continue, we reach the convergence. Perfect. Now, this is a function that is used in policy improvement. The idea is that in the policy improvement, we start saying that the policy is stable, okay? So that the policy reached the convergence. We imagine that this happens at the start of the algorithm. After that, for each state that belongs to our world, what we do is to store, okay, the old policy that we compute, and we evaluate the policy with the value that we computed before. Okay, here there is a kind of missing in this pseudo algorithm because there are a lot of versions of this, but the reality is policy evaluation is called here in the first line of the algorithm. So however, the idea is that when we notice that the old action, okay, which was the old policy, is different from the new, what means? It means that we found an action which is the best. We find a policy which is optimal than the previous policy just computed by us. So the policy is not stable. We didn't reach the convergence, and what we done? We go to the point 2. We start again to compute the value function, and this process continuously till the convergence, till the moment where we have that the old policy is equal to the new computed. So it means that we reach the convergence, the algorithm stops, and we found an optimal policy. The key idea which is the difference between the value iteration of before and the policy iteration of now, is that while before in the value iteration we compute the value function during the iteration and only at the end we extract which is the policy. Here in the policy iteration we tried before to compute the policy, try to use the computed policy to we compute the value function, and after we use this value function to compute the policy. If we do not achieve the convergence, again we used the policy to compute the value function, and here we use the value function that we just compute to compute the policy. It's a ping pong between the policy substantially and the value function. Usually it is, at least about what I see, in my experience, reach a convergence more faster than the value iteration, probably due to this ping pong of check which is the best in some sense. Okay, having said that, there is bad news for you in the sense that the world is not so easy, and in reality, the transition probability in the real world is not known. This is usually it's not known, or better, sometimes we know properly which are the transition probability, okay, go from one state to another. But usually in the real world, it's not possible to know this. So this kind of algorithm that I explained to you are useful to start to understand, to enter in the concept, are useful for some problems where we know the probability transition, the transition probability of each state, but concretely speaking, it's difficult to find a real problem where to apply them. To be sincere. Okay, and now we can have a break. If there are questions, of course, now after whenever you want. How much do you prefer? For me, it's not a problem, and I go the stage to Lorenzo, who will explain to you the strong part.
Okay. So up until now, we have assumed that we know the transition probability and the reward function. So we can directly take that and ask it, like, what is the probability of ending up in a state given that I performed that action and I was in that state? But in reality, those assumptions are not real, because in the real world, we actually don't know the probability of going into a state. If we are in a setting where those assumptions are real, we can call that model-based. So model-based algorithms assume that we have a model of the environment, so that we know those two things. But now we will talk about model-free reinforcement learning, which is a family of algorithms which assume that those two are not knowns, and we will learn purely by trial and error. So as we said before, the value function is computed with the Bellman equation, which needs the probability. So the value function, the value of a state, is the expected value, the expected reward of that state. So it's a summation of the rewards weighted by the probability of getting that reward. But how can we compute that if we don't have the probability? The Monte Carlo principle comes to help us, because this tells us that if we have a function which we can draw samples from it, the samples that we will draw from it will be distributed according to the underlying probability. So this is a stupid example. Like, if you don't know the distribution of the samples of this function, but you have a way to draw sample from that function, you'll see that most of the samples will be there, because the probability of getting a sample there is higher than the other places. So this is the expected value, but we don't know the probability. So we can approximately have it by computing the average. of the samples. So we draw samples, and as the number of samples increases, the value should converge to the expectation. So we take the samples and we compute the average. This average will be the expected value. From now on, we assume that we can compute the expectation in this way. So as I said before, we now have that the value of a state is simply the average over the samples, where the samples, for example, we have n samples. Each sample is the reward. We get the reward by using our policy to collect samples. So we take our policy, we perform an action into the environment, and we observe what happens. We observe the reward that the environment gives us by performing that action. This simply means that we are in a state, we use the policy, the function policy pi, we ask it, which is the action I need to perform, okay? And I see which is the reward I get. Then each sample is simply the immediate reward plus the discounted future reward. Since this is an estimate, okay, this is our current estimate. And we update iteratively our estimate by taking samples. So we take a sample, we sum it with the next sample, etc., to compute the estimate. This is the pseudocode of the Monte Carlo algorithm. So it starts by initializing a policy randomly, okay? We initialize the Q table, which is a table which stores the estimated Q value for each state action pair, and a list of returns for each state action. So initially, we choose our start in a random state and with a random action, since our policy is not good in the start case, since it's random. And we need to generate an episode. An episode is simply a sequence of states and actions. You see there, you are in an initial state, you perform an action, you see the reward, and you go on until you reach a terminal state. So once you have that episode, you have that sequence of state, action, and rewards. You can compute the return. The return is this G. Then from the end of the episode, you compute the return backward. So you start from the last reward you obtained, and you go backward till the first reward you obtained. And you compute the return for that trajectory, for that episode. For each step in the episode, starting from the last step, you take the immediate reward and plus the discounted return you obtained so far. So for the last step, it is 0, G is 0, so you get only the immediate reward. But like if you go at t minus 2, you get the immediate reward plus the discounted return of t minus 1. Then you append this return to the list we have here at the position of the state and the action we are in, okay? Then the Q value will be simply the average of the returns. This comes from this. What we've seen before, the value is the average of the returns. And the policy will be the action which maximizes this Q. So we look for a given state at all the actions, and we look at the Q values of each action we have computed so far, and we say, okay, those are the action I can perform. Which is the best action I can perform? The best action I can perform is the one with the highest Q value, since the Q value is the goodness of an action, the expected reward I get in future. So since the goal of reinforcement learning is to maximize the reward, we want to choose the action which on average will bring us the highest reward, the highest Q value. This algorithm has a problem. The problem is that you update the policy only at the end of an episode. But this is slow. We want to do it faster. And because an episode might be really long and might take a lot of time to generate. And there comes temporal difference. Temporal difference computes updates the policy at each step. And it uses a running average. Okay, a running average is simply a weighted summation. You say this is the previous estimate of the value of a given state. And we say, okay, our new estimate will be 1 minus alpha, where alpha is a constant, which we set, which is the weight of the new, this is the new estimate, okay? So you weight the new estimate by alpha and the old estimate by 1 minus alpha. By simply rearranging this, we get to this, which is the same thing. And here comes the temporal difference. Okay. So you take the old estimate plus alpha times the error I'm making. This is my current estimate. This is my new estimate. So how wrong am I? So I say, okay, given that I assume sample to be my new estimate, my new the new estimate for the value function, I say, how wrong am I? And I'm updating my estimate by this. Since we are still computing it, okay, I'm not adding this simply, I'm weighting it, okay, because I might be wrong. This estimate might be wrong. So we update not totally, but with a weight. And simply this expanded is this, where sample, so our new estimate is the immediate reward plus the discounted future reward. So the new estimate is the old estimate plus alpha times the immediate reward plus gamma times the estimate for the next state minus the old estimate for the current state. When this is zero, all the parentheses is zero, we reached the convergence. So when we have alpha times zero, we reach the convergence. And so we know that the value is right. We have reached the right value function. And this same concept can be applied to Q value. So we can estimate the Q value in the same way. So we have Q new, Q old, Q old, Q old, the same thing. And in each state, we have that the value of a state is the maximum over all the Q values. And this is the equation for the Q value. But we know we don't have the transition probability, but we will compute it by averaging over the samples simply. The first temporal difference algorithms I will present you is called SARSA. SARSA stands for state, action, reward, state, action. The authors of the algorithm had much fantasy, so they call it so. So first, you initialize the Q table arbitrarily. Since you don't know, you can set it randomly or to 0 is the same. You start. So the difference between temporal difference and Monte Carlo is that you update the policy at each step. So you perform a step, you update the Q value. Okay. SARSA is called on policy. It means that it updates the Q value with the same policy that it uses to generate the sample. So you see there, it generates a sample. Like there. You take an action and you observe R and S prime. And this action is chosen according to the Q values. Okay. There, you choose A prime and use here A prime, but again, this is chosen from Q. Like you are updating the Q value by using the same policy you're using to generate the samples. And this is called on policy. And you loop on it, you generate n episodes, and for each episode, for each step in the episode, you update the Q value. The second algorithm is Q learning, which it's really similar to SARSA. The only difference is here. So while in SARSA, you update the Q value with the same policy you use to generate samples. Okay. Here you use the maximum. So this is the only difference between the two algorithms. Okay.
Also take the average. You go back.
No, it uses the Q value of the action chosen previously. So you use the policy to choose an action, and then you use the Q value of that action to update the current estimate. While in Q learning, you use the maximum over all the actions. So you don't use this action which you have taken from the policy. You don't use the policy, the action given to you by the policy. You use the maximum. You have like this maximum is like another policy you're using. It's called the greedy policy, because you are acting greedily. Like you have the Q values, and you choose the one, the higher one, the highest one. So this policy is different from the policy that generated that action. Yeah. SARSA is not taking the maximum. This might be the maximum, but it might not be the maximum. This is you choose an action based on the Q values, but here it says, for example, epsilon greedy. Epsilon greedy is a strategy which a certain probability epsilon you behave according greedily. So I rephrase. You have epsilon greedy, which is a strategy, a policy, where with a probability epsilon, you act randomly. It's like you have 10 actions with a probability epsilon, for example, 0.3. So 30% of the time, you'll behave randomly, and 70% of the time, you'll behave greedily. So 70% of the time, you choose the action which maximizes the Q value, the argmax over the Q value, and 30% of the time you will act randomly. So it might be that you are in the 30% case, and this is not the greedy action. This is the random action. So you're updating, and this might not be the best action. So you're updating the current estimate with an action which might not be optimal.
The thing that I get, SARSA just at the epsilon value. So when the epsilon is 0, SARSA is equals like
yeah,
Q learning.
Yeah.
When we are completely greedy, it means we are doing Q learning.
Yeah. But if here you have a policy that is not only epsilon greedy, you can have any strategy you want. Epsilon greedy is the simplest example, but the thing is this, that in SARSA you use the same policy to generate samples and to update the to update the policy, while in Q-learning, you generate samples by using a policy, but then you use a different policy to update the value. Is it clear?
Yeah.
Okay. And in practice, those two algorithms, in reality, those two algorithms behave almost similarly. But SARSA usually is more conservative in the sense that, for example, this toy problem is called the cliff, and it's a stochastic problem. So if you go there, there is a small probability to go into the cliff, and you have a better word. Here you see it, -100. If you go into the cliff, you get -100, but you have a cost for each step you do in the environment. So if you do this, you get -1. If you do this, you get -1. So you get -1 for each step you perform into the environment. So since you want to maximize your return, the summation of your rewards, okay, in the end, the smart thing to do is to do the minimum number of steps possible. So this is the shortest path, the path which achieves the minimum return, okay? But this is dangerous because you could fall into the cliff. And SARSA understood this, so it does a safer path to reach the goal, while Q-learning, acting greedily, learns to behave in a way that might not be safe because it could fall into the cliff. This is the sum of rewards during the training, and you can see that the SARSA has a higher sum of rewards because it avoids actions. So it avoids ending up in states that might bring you a better reward. So by doing this, it avoids the cliff, and so it avoids the reward of -100. Those two algorithms have a problem, which is that they need to visit all the states and action pairs to actually have a good estimate. And also they need to keep in memory all the key values for all the states and actions. And if you have a huge state space, for example, you have 1,000 states, and you have, for example, 10 actions for each state, you have 10,000 possible values entries in your table. And to compute the value, a good estimate for each of the 10,000 values might take a lot of time, and also maybe 10,000 is stays in memory, okay, but maybe you have 10,000 states and 10,000 actions for each state, and this will explode, and you cannot fit that in memory. Another approach is called Monte Carlo research, and this algorithm combines the Monte Carlo principle we have seen, the Monte Carlo algorithms we have seen before, with tree search. And if you don't know what is a tree, you can look outside. You can see those green things. Those are trees. Jokes aside, this is a tree. In computer science, we call tree a structure, a data structures, which is composed by a root. A root is the head of the tree. Each node has some childs. Here you see this is the root. This is a node. It has 3 childs, and it grows below from the root to the leaves. The leaves are the nodes with no child. If a node has no child, it's called leaf. And these structures resembles natural trees, but they're in the opposite. So usually in natural trees, you find the root in the bottom and the leaf on the top. In computer science, we are strange, so we do the tree on the opposite. And Monte Carlo search is composed of 4 phases, which continuously repeats. You cycle along those 4 phases. The first phase is called selection. So you start from the root node and you choose an action by using a tree policy. We'll see later what is this policy. For the moment, imagine you have an oracle, you have a function, which given a state, which given a node, which tells you which is the action you need to perform. In this tree, the white nodes are the states, and the black nodes are the actions. So we continue selecting actions in this tree until we reach a leaf node. At the starting of the algorithm has only the root and is its free child. The algorithm starts with the root, which is the current state you are in, and the actions you can perform from that state. I think that I forgot to mention is that this algorithm is an online algorithm, which is really simple to understand. Like instead of computing the policy for all possible states, you care only about your current state. So if you're in a state you want to compute the policy for the near future. So you compute the policy for today. Then, for example, I need to move from there to there. So I compute how to move now. Then I move and I recompute how to move, where to move in reality. Like I'm here, I say I compute the policy, and the policy says me move forward. Okay, then I recompute the policy, move forward, and so on. This is online. So at each state, I recompute the policy. I recompute how to move. Yeah. Yeah. This tree is not really representing like we can have this yeah, that's true. Yeah. Since we don't know the transition probability, like for example, I can draw it on the board. Like you have a state, and then you have your actions. And when you perform an action, since you don't know the transition probability, you might have more than one state. And the way it works is that you don't choose the state you'll end up, but the environment will tell you. So you perform this action, and the environment will tell you, okay, you go there, or like you go there, or you go there, for example. No, because you perform an action and you have feedback from the environment. You see, the environment tells you in which state you end up. Like in all reinforcement learning, you perform an action and you see the outcome. You see the state you end up.
Algorithms because the outcome is not certain. So you try to perform an
Yeah.
action, and then you end up in a state which might not be the one expected, and so you perform the policy again.
Also, if online algorithms, you can compute a partial policy. You can compute a policy for the near states, and like in less time compared. Like if you want to compute the policy for all the states, maybe You need a lot of time, but you are interested in finding the policy for the near future.
So next 10 steps forward.
Yeah.
And 10 steps forward.
Yeah.
Okay, rather than doing a million steps.
Yeah.
Which will take so
Yeah.
then you have certainty.
Yeah, also this. So in the selection phase, until we reach a leaf node, for example, we reach here the leaf node, and once we reach the leaf node, we do the second phase, which is called expansion. As the name suggests, expansion is simply expanding the tree. So you add new nodes to a tree. For example, if we are in this state, you can add its actions. Then, once we have added the new nodes to the tree, you can perform the third step, which is the simulation phase. This is sometimes called rollout or playout. In literature, you can find it behind various names. Here we call it simulation, but you can, if you hear rollout or you hear playout, they are the same. In principle, it is simply like starting from the node you have expanded. You perform a trajectory. So you start from the node you have expanded by using a rollout policy, which is a policy you have, like you can choose it. It's a parameter of the algorithm. For example, the simplest policy I can think of is the random policy, in which you choose randomly an action. This is done to explore the environment. In reinforcement learning, you have two key concepts, which is the trade-off between exploration and exploitation. What does it mean? Since we don't know the real value of the action, we need to estimate it. We're estimating it from samples, but since it is an estimate, it might be wrong. We might be wrong. So if we choose every time the action with the highest Q value, we will ignore other actions. Because if you have 10 actions, so you perform the first. So in this imagine, I'm the agent, and this is my environment. If I do the forward action, I might get a reward of 10, for example. Okay, cool. So I could say, oh, I do every time forward, but this I might get lucky. So if I try to do forward another time, I might get -1. And maybe other actions are more good than this one. But if I haven't seen them, I cannot know it. So we have this concept of exploitation, which is I select the action which has the highest Q value, and exploration, which means I sample new trajectories, I sample new states, I visit new states, I try new things. Another example is like you want to choose the best restaurant in town. How you know it is the best restaurant in town for you? The best restaurant in town could be thought as the restaurant which brings you the most happiness. But you need first to try every restaurant sometimes before you know how happy makes you. So this is the concept of exploration. You visit each restaurant a number of times, and then you know how much happiness it brings you. So in this case, the rollout is simply exploring the environment. So you use this policy to perform actions in the environment, and when you perform those actions, you do not add the state you visit to the tree, but you forget about the states you visit, and you keep only the return, the reward. Like each time you get a reward, you sum it with the discount factor. So you take reward 1 plus gamma, which is the discount factor, times the reward plus gamma squared times the next reward, etc. And the last phase is called backup. backup is sometimes you can find it called backpropagation. Is simply once you ended up the rollout pulse, the rollout phase, so you reach the terminal state, or for example, you say after 100 step, stop. Okay, so you end up the simulation phase. You take the discounted sum of rewards you get, and you backup it. This means that I have a value here. I traverse the tree backward to the root. So in the tree phase, in the selection phase, we traverse the tree from the root to the left. Here we do the opposite. We know the path we have done before, and we perform we traverse the tree backward. By doing so, we update in each action node contains a statistic, which is the contains a value, okay, which is the sum of returns. So when you traverse the tree backward, you update that. So for example, if we are in this simple example, okay, maybe you do rollout here, and you get 100. This is G, because is the G is simply R plus gamma R2 plus gamma squared R3, etc., etc. So assume this is 100, okay? And to get there, you have done this. So you take this value, you go to the last action node you have performed, okay? And you update its value. It's not the value, it's the return obtained so far. So the R of this node will be the immediate reward you obtain by performing this action and ending up in this state, summed with the discount factor with G, okay? And assuming, for example, we have another state here and another action here, okay? So this is another action, this is another state. This, we backup this value even more. So from here, we backup the value here, okay? And from here, we backup the value here. So this will be updated with the immediate reward plus gamma G, but this time G is this one. So at each step, you update, you sum to the G, the current reward. Like this G is this. Each node add its own reward and gives that value to the node before. We do recursively. Yeah. So from here, you take the sum of discounted return you obtain, you give it there, you update it, and you sum the immediate reward obtained by this action, and this value is given to this, which adds which updates is sum of returns, and gives the value to this one recursively, etc., until we reach the root. It's clear? And the whole process is repeated n times. So since at the start the tree is empty, I mean, we want to construct a tree a bit. So we perform all this cycle n times. I think I didn't say about Monte Carlo search is that it is a model-based algorithm. So it assumes to have a model of the behavior of the environment. So before performing an action, for example, before I move forward, I need to decide what I want to do. To do so, I interact with the environment. I interact with the environment by constructing the tree. This is done by interacting with the environment. So, but not with the real environment. I'm using a simulated environment. You can imagine like your agent needs to drive a boat, and before deciding how to behave, it has a model, which might be a game in Unity, for example, with which it interacts, and it learns in that moment how to behave, and then it performs the action. And then again, for the next action, it interacts with the simulated environment and decides how to behave. Another example might be that, for example, when you have to go from your home to here, you don't perform like you think in your mind, how is the road? What are the obstacles in the road, etc. So this thinking about the way you want to behave is like simulating with a model. The model is your brain. Your brain models the word, and so you like simulate with your brain the road you will perform to reach to go there, to go here, okay? And so you say, okay, I know that in Via Centro, there is a tube that exploded, so I cannot go there. And I'll do another road. But the thing is that you simulated the road you will perform. So you already know what is the action to do, since you simulated many trajectories to come here. And you say, okay, this is the right road, since it is the highest Q value, or like the fastest one. So yeah, you simulate and then you perform the action, then you simulate again and perform the action. I think I forgot to say is that once you constructed the tree, you at the end, once this ended, you have a tree, and to choose the action to perform in the environment, you have an estimate of the Q value of each node, which is simply the sum of the returns we have computed by doing this backup, okay? Then for each node, you have the number of times you ended up in this node, okay? As in Monte Carlo, by computing the average of the returns, okay, you do the summation of all the returns you obtained by ending up in that state and performing that action, and you divide that by the number of times you visited that action, okay? And you compute the estimate for the Q value. The Q value is the sum of the reward, the returns, divided by the number of times you visited that action. The tree policy is called UCT, which stands for upper confidence bound applied to trees. And it is an equation which you compute for each action node. Given a state, you have child nodes, which are actions, and each node has its count of the number of time it has been visited. And for each action node, you compute the UCT value, and you choose the node which has the highest UCT value. The UCT equation seems really strange, but in reality, it's really simple. So you have two main parts. The first is the Q value, the estimated Q value, which, as we said before, is the average of the returns. But this is an estimate. This might be wrong, as we said before. This incentivizes exploitation, since our goal is to, in the real world, to have the highest return. We want the Q value estimates this one. So choosing the action with the highest Q value, in theory, should bring us the highest payoff, the highest return. But those are estimates. Those might be wrong. And we want also to visit new actions, to try new actions, other actions that we have never performed or performed not that much. And so we add this term, which there you have the natural logarithm of the number of visits of the parent. And there you have the number of visits of the action node. The logarithm is used so that when you reach a certain number of visits of that node, you don't care about visiting that again. For example, if you visit a restaurant 1,000 times, then you are quite sure about the happiness it brings you. So at certain times, the incentive for exploring that restaurant, that state, will be constant. Then you divide by each the number of visits of each child, because you want to distribute like the number of visits like almost equally to the child. And this if this term is 0, this goes to infinity. So if so we are sure that we'll see each action at least once. And so these terms incentivize to try new actions. This term incentivizes to you perform actions that we know that are good. So exploit, explore. And this is simply an hyperparameter of the algorithm, which is set empirically. You need to try various values, as always in machine learning. And you this is useful because it balances the two parts. It balances the exploitation and exploration part. Monte Carlo search, unfortunately, has a problem. For a complex environment, it might require a lot of simulation, so you need to perform the 4 phases many times. And also, if you have a large state space, the tree will be flat. And this is not good because you haven't seen new states, okay? And the policy will be not good. I mean, if you have a number of simulation, which is like 100, and you have 1,000 states, 1,000 nodes, you won't see each node equally. You won't see, you will see only 100 states, but there are 1,000. So you cannot have a good estimate for the Q value. What's next? So till now, we have seen what we call tabular methods, which are methods that like keep some sort of table or like keep in memory a value for each action state pair. But as we said before, if you have like 10,000 states and 10,000 actions for each state, it might be a problem. You cannot compute this number. You cannot keep in memory this huge matrix. So the thing we will see next week will be how to approximate the policy and the Q function. So how to have some sort of black box some sort of function, which we give it the state or the state and action pair, and it will tell us the Q value, the goodness of the state action pair. That's it. Thanks for your attention.